Before we do that, though, let's take some questions from Homeworks. Zach.
Meeting number 41.
Yeah, sure, man. So 41 says an agency drops food containers from an airplane on war-torn famine area. The drop was made from altitude of 1,000 feet above the ground. Write an equation to model the height in feet of the container during free fall, function of time t. All right. So hopefully you recognize in this problem from the context of it, this is a one-dimensional problem where things aren't moving left or right, it's just going straight down. So we just need to use the one-dimensional version. So that's negative 16t squared plus the initial velocity, which is 0 if it's being dropped from an airplane. It's not being shot up in the sky or anything, so it's like 0t. And then plus the initial height, which said was 1,000. And then part B says after 4 seconds of free fall, the parachute's open, show how many feet above the ground, blah, 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 when that happens. So basically we're just doing y of 4. And that's just punch that bad boy into your calculator. Let's see, that's negative 256, so like 744, it sounds like. Just trying mental math there. If that's not right, I apologize. I think it's, though, might be. 16 times 16 is 256, right? Yeah. So 1,000 minus 256, 744. I think that's right. Zach, you feel good? Lexi? 28? Oh, 48. Okay. I was like, oh no, I wasn't prepared to go all the way back to that page, although you certainly could have. So it says Nick hits a golf ball off a practice tee with initial velocity of 100 feet per second with 4 different clubs. How far down the fairway does the ball hit the ground if it comes off the club, making the specified angle with the ground? Okay, so initial velocity times cosine of the angle t. Y of t is negative 16t squared plus initial velocity sine of the angle times t. And I guess the practice t height is basically going to be 0. Doesn't give me any information about that, so I'll assume we're just hitting them off the ground or whatever. The height is so small it's negligible. So all I'm going to do is just take that equation for y, set it equal to 0, because that's going to tell me the time it takes for the ball to hit the ground. And then I'm going to take that answer and then plug it into the x to get how far the ball goes. Is that okay? So to solve this guy, this actually becomes pretty easy since there's no constant term. You could solve this by factoring. So one of them is t equals 0. The other would be negative 180 sine 35 divided by negative 16. So that's me having my calculator in radian mode. I was like, that's not right. Try that again. So 6.45 seconds, it's in the air. So 180 times cosine 35 times the answer, 951 feet. And golfers in the room, 951 feet for a golf shot, plausible. It's like 300 yards, right? That's far, but like you can do it if you're good at golf or whatever. I can't do it, but
35.
Is it? I don't know the club, what kind of club that makes it. Lexi, does that feel okay? And then obviously it has 3 more parts, but all you're doing is just changing the number there and repeating the exact same process. You know what I mean? Does that feel okay? You sure?
Yeah.
Okay. Just want to double check. You seemed not super satisfied.
It's a lot of work.
It's a hassle. Yeah. But really, I didn't write that much down. You know, like, if you really want to do it, just make this alpha the whole way through and then just write down 4 answers. It's the same work over and over and over again. And just do it all on your calculator and just put an angle measure there. Because this work doesn't change, you know. Does that feel any better? Is Mr. Kulik finding a way for you to write less?
Yes.
Sure. Jack, what's up?
Can you do 54?
Sure. So it says, find all the polar coordinates equivalent to this point. So you have everything that's coterminal to this point, right?
Yeah.
Or you can have the things that are negative. So we're going to take our initial angle, add 180 to that, and then add 2 pi k. So that just simplifies down to really pi over 6 plus 2 pi k, where k is just some integer. But that's it.
All right.
Is that okay?
Yeah.
Sure. Zach.
Can you do number 50?
Yeah, do we have to plot all the points or just like some of them or?
Just like W and Y.
Okay.
Or W and Z.
Okay. So W is -5, -135. So I'm going to start by adding 360 to the -135 to make that 225, just because it's a little bit easier for me to do positive angles than negative angles. So I go and I count around, so 0, 30, 60, 90, 120, 150, 180, 210, and then 240. So like halfway in between here is 225. But it's -5, so I know I'm really going to be flipping over to that side. And then I just count 5 circles. So 1, 2, 3, 4, 5. So there's my W.
So if it was positive, it would go in the same direction as the angle.
Yep. And did you say you need to do another one?
Yes.
Okay. So I'm going to do the same thing. I'm going to add 2 pi to 9 pi over 4 until it gets to a positive angle. So I had to add 2 pi twice. 7 pi over 4, which is the same thing as, and I'm going to convert this into degrees because the denominator isn't 3 or 6. It doesn't end on one of the grid lines. So it's going to be easier for me to figure out where it goes in between if I just have the degrees rather than the radians. So that's 315. So let's see. This was 270, 300, 330. So 315 is like right in there. but we're negative on the r. So I know that I'm going to flip it across. And then we're counting 6 circles down. 1, 2, 3, 4, 5, 6. Cool. All right. Rock and roll, dudes. Anybody else? Okay, Majokes. Today, we're going to finish up chapter 10. So we're going to do 10.4 and 10.5. In 10.4, we're going to start by talking about polar functions. Last time we met, we talked about the polar coordinate system and how to convert back and forth between polar and rectangular coordinates. We're going to start today talking about how we convert back and forth between polar functions and rectangular functions. Here's the good news. The tools we're going to use to do that conversion, they're the same tools we're going to use to do the coordinate changes. So there's nothing new there. So we have that x is equal to r cosine theta, y is equal to r sine theta, and then x squared plus y squared equals r squared, and tan theta is equal to y over x. So those are the same 4 tools that we use to convert back and forth between polar coordinates and rectangular coordinates. They're the same 4 tools we're going to use converting back and forth between polar functions and rectangular functions, which is nice, right? Nothing new there. Let's go ahead and look at an example. So an example of a polar function would be something written r equals 6 cosecant theta. Typically, when we write a polar function, r is written as the independent variable and theta is written as the dependent variable, much like we've done here. So my goal here is going to be using the x equals and y equals probably to convert this, get rid of the r and theta. So what I'm going to do straight away is I see I have cosecant, and in none of my conversions is there a cosecant. So I would start by rewriting that in terms of sine and cosine. Anybody remember what cosecant is in terms of sine and cosine? One over sine. There you go. Those identities coming back. They never really went away. And then I notice if I multiply both sides now by sine theta, what is r sine theta equal to? It's y. Right? Y is equal to r sine theta. So r sine theta is just y. So I'm done. Oh, that's okay. So what does the graph of this look like? It's a horizontal line, right? Let's just kind of confirm that. So we're going to change our calculator to polar mode. I'm going to change from degrees back to radians. And now if I go and I look at my y equals menu, it starts with r equals. And I can't do, my calculator doesn't have a cosecant button. So I'm just going to write 6 divided by sine theta. And then let's take a look at my window and make sure that's just sensible. Theta going from 0 to 2 pi, that looks good. And we're plotting it on a standard window from -10 to +10. That seems fine. I hit graph, and shockingly, it's a horizontal line. Looks like y equals 6. I know. Everybody feel okay there? Yeah, right? Not so bad. Mr. Kulik, does it get harder than this? Well, yeah, of course. What if we have r equals 6 cosine theta? Now, if we try to do the same thing we did before, maybe we tried to divide both sides by cosine theta. But if we do that, we're not going to get r times cosine theta. We'll get r over cosine theta, which is not x. Or if we tried to move the r to the other side, kind of the same thing's going to happen. We'll get cosine theta over r. So there's not going to be a way that using like just dividing or multiplying things to both sides, I'm going to be able to get that r and cosine theta together on the same side, right? So we're going to have to take a different tact to that. So before we do that, maybe let's just take a look at the picture and try to see what it is that we're trying to build here, right? Sometimes that can be helpful. So make that 6 times cosine theta. Aha! What does this appear to be? Circle, huh? So I should have, in my equation, I should have like an x squared and a y squared in there, right? And that to me is a big hint. So what I'm going to do now, and I'm going to multiply both sides by r. Why would Mr. Kulik want to do that? Well, for one, on the right-hand side now, I have r cosine theta. What's r cosine theta equal to? X. Secondly, on the left-hand side, I have r squared. What is r squared equal to? X squared plus y squared. Right? You guys see it there? Okay. That's looking a little bit better. We've cleared out the r's and the thetas, right? The problem is that if this is a circle, looked like the center was at 3, 0, and the radius looked like 3. I need to somehow get this into the form of a circle. So I'm going to go ahead and move all the x's and y's together onto the same side. And if you remember the equation for a circle, x minus h squared plus y minus k squared is equal to r squared. So somehow I'm going to need to take this x minus 6 piece and get it to look like this. Or x minus 6x piece and make it look like that. Is everybody okay with that? Now you learned how to do this last year in your Algebra 2 class. Does anybody remember the name of the process we used to do that? The initials for that process are CTS. Does that ring any bells? Completing the square. Very good. So the idea behind completing the square is we're going to take advantage of the perfect square factoring pattern. Is we're going to try to build a quadratic that looks like a squared plus 2ab plus b squared. So right now, looking at this, x squared is got to be the same thing as a squared, right? And that means negative 6x has to be the same thing as 2ab. Everybody agree with that? So what's b have to be? B has to be 3. So if I know that if a squared is x squared, a is x, right? So I know 2b is negative 6. So b is negative 6 over 2, or negative 3. Okay? So what I'm going to do is I'm going to add negative 6 over 2 squared to both sides. And I could write that as negative 3 squared also, but since these are notes, I'm going to write it as negative 6 over 2, so hopefully it's a little bit easier to see where it's coming from. Now, if I take that quadratic, this factors, everybody's okay there? And really, this is just what we're looking for. So, Mr. Kulik, when I want to complete the square, then I'm just going to take the coefficient from the linear term and divide it by 2, and then square that and add it to both sides. Yep. Well, I should say, as long as the leading coefficient on the squared term is 1, which will always be in our case, then yes. If the leading coefficient on the x squared term or the squared term isn't 1, it's a little bit more complicated than what we just did, but we don't have to worry about that situation. So let's not worry about it, right? Who's worried? Do I sound worried? No. Okay, let's do one more. Mr. Kulik, does it get harder than this? I mean, like, not really, but, you know, this would be the worst case scenario right here, which I don't really think is much harder than the previous situation we just did, but, like, whatever. Notice right away that there's not going to be a good way to get the r and the cosine directly together, right? I can't just add or subtract or divide sines and cosines to get the r and the cosine theta or sine theta directly together, right? You guys agree? So we'll do the same trick. I'm just going to multiply both sides by r. So I see 3 things that I can do. R squared is x squared plus y squared. R cosine theta is x. And r sine theta is y. Cool beans? Just like before, I'm going to move everything onto the same side. I'm going to group the x's together. And then I'm going to group the y's together. So far, so good. What do I need to add to both sides to complete the square for 5 or for x squared plus 5x? I need to add 5 over 2 squared to both sides. And then what do I need to add to both sides to complete the square for the y's? Negative 4 over 2 squared, or you could just write that as negative 2 if you prefer. These are notes though, so I'm going to try to write it in like the way that it's obvious to see where I got it from. We doing okay? Now the nice part about the completing the square is that we know exactly how these quadratics factor. So we really have then x plus 5 over 2 squared plus y minus 2 squared equals 41 over 4. Now this problem really, I think, illustrates something quite effectively. Now, the previous problem that we looked at, arguably, you could have said, well, Mr. Kulik, why did I bother doing all that completing the square stuff? I could have looked at this picture and gone, center's 3, 0, radius is 3. I'm just going to write the equation for the circle instead of jumping through all those stupid hoops that I just jumped through to complete the square, right? Reasonable comment. The answer to that is, well, what if you run into something like this situation, like we had in this problem? The center here would be at 2.5 comma 2. Maybe reasonable you come up with that, but the radius would be at square root 41 over 2. Good luck reading that off your calculator, right? So if you actually want the exact equation, tough to get that just from looking at the picture on your calculator if the radius is like a radical or something. You know what I mean? Here you're kind of stuck having to complete the square to be able to get that exact value. So far, so good? It's okay? What if we want to go the reverse direction? What if we want to go from a Cartesian or rectangular and go back to a polar? Well, let's start with something simple. Let's say we have y equals 4. Uh-oh. I don't know why banging the desk seems to always bring it back when it does that. Okay. Well, I need to get an r and a theta in here, correct? What do I know y is equal to? It's r sine theta. And typically with a polar function, you leave the r by itself as the independent variable. So let's just divide the sine theta over. So you could write as 4 over sine theta or 4 cosecant theta. Either is really fine. That's it. That was pretty easy, right? No big deal. Mr. Kulik, does it get worse than that? Well, I mean, like, kind of, but I don't think this is really so bad. What if we have this guy? What should I do first here? Anybody got any ideas? Looking for that risk taker to volunteer an idea here. It's okay to be wrong, even if you don't know what to do exactly. I know it seems like everybody that answers questions has the right answer every time the first time out, and it gets intimidating. But like, we're all guessing here. None of you guys have done this before. You know, what's your instincts say? That's a great idea. Let's FOIL that out, right? So when I FOIL this out, what do I get? I get x squared minus 9 plus x squared plus 36 equals 45, right? No! It's very sad if you write this down. When Mr. Kulik was grading the homework quizzes, he got very sad many times. I saw lots of foiling like this. What's wrong with what we did here? You distributed the exponents. You didn't actually FOIL here. What should we be getting? Yeah. You got to make sure you're FOILing out. Everybody's okay with that? What do you want to do now? Sure, what like terms do we have to combine? Okay, I'm actually going to do it this way and just move it all onto one side. So I just have the 0 over there. Actually, what else do you see? There's some other stuff we can do.
Do the x squared plus y squared to get the y squared.
Yup. That's good. What else do you see? You could. It doesn't help, so we're not going to do it. But yeah, that's true. You could do that. Not helpful, but it's true. Wouldn't be wrong. What are we trying to do here? The goal is to get rid of all the x's and y's, so you have just r's and thetas, right? What do we have left that we still need to deal with? I have a 6 here, or I have an x there and a y there, right? Yeah, so Paul says x is just r cosine theta, and y is just r sine theta. Okay, great. What should we do now? Well, I would leave the r squared where it is, and I'm just going to move and add the other two pieces, or add or subtract the other pieces over to the other side. Now we're very close, right? This should be r equals something and just thetas. Here we have r squared equals r times something theta minus r times something theta. What are we going to do? Divide by r. That's correct. Wait a minute, Mr. Kulik. You just said that's correct? we're not supposed to be dividing by variables. You've told us that many times that that's not something that's okay to do. Yet you just said it was okay to do it here, and you said it was correct, which makes me kind of angry. Why is it okay in this situation? Why don't we want to divide by variables typically? Could be 0. Absolutely. Can R be 0? No, man. Why? R is the distance to the points on that circle, right? Can that be 0? No, man, it's a circle, right? Can't be 0 distance, right? So it's okay because we know that R is non-zero. What do you guys think? I'd argue this was easier than going the reverse direction, turning things from Cartesian or from rectangular to polar, since here all you had to do was FOIL. There's no completing the square necessary, which I think is a little bit tougher than foiling. Maybe just a little. But that's it for 10-4, right? Just going back and forth. We use the calculator to generate the graphs. We're not going to do any graphing by hand. You know? So in 10.5, we're going to be talking about graphs of polar functions. So to start off, I want to talk about some attributes like mins and maxes and domain and ranges and symmetry, stuff like that. So let's just look at an example here. Let's say we have the polar function r is equal to 3 plus cosine theta. And let's start, say, just being interested in the mins and the maxes. So when we say the min and the max, we're talking about like the minimum value r can have and the maximum value r can have, since it's an independent variable. So if I look at this equation, the minimum and maximum values of r are really dependent on cosine theta, right? Wherever cosine theta is at the minimum, r would be at its minimum. And wherever cosine theta is at its maximum, r would have to be at its maximum, since they're just adding 3 to whatever that is. Does that make sense? Okay. So what is the range of values for cosine theta? This is something you should know. We studied this first semester. What's the minimum value cosine theta can have? Think about the unit circle. Not 0. -1, 2. +1 is the range for cosine, right? At 180 degrees, cosine is -1. The x-coordinate's -1. At 0 degrees, cosine's at +1. The x-coordinate's +1, right? We can picture it now once I say it, and you're like, oh yeah, I definitely knew that, but I couldn't come up with it because I wasn't thinking about it in the right way, but that's okay. So really, the minimum value here is going to be 2, and the maximum value would be 4. So the range for this function then, r is going to go from 2 to 4. Everybody's okay with that? What's the domain for this function going to be? Well, the independent variable there is theta, right? That's the one we have our choice of. So really, the domain for this function is going to be the same as the domain for cosine theta. Everybody agree with that? Since if we can plug it into cosine theta and get a value back, we can plug it into R, we can plug those same things into R, right? Or R of theta, if you want to think about it that way. So anybody remember the domain for cosine? Again, we did this first semester. It was a major result. We spent like 2 chapters building out our definitions of sine and cosine. What kind of numbers can we plug in for sine and cosine? All real numbers. That was the point, right? We started with sine and cosine defined only inside of a right triangle from 0 to 90 degrees. And we spent like 2 chapters building out that definition so you could literally plug anything into sine and cosine you want and get a value back. Everybody remember doing that? Okay. All right. You guys feel okay about doing like a domain and range and min and max for something like this? Let me see one more example. What do you guys say? You got it? It's all right? All right. So the thing we haven't talked about here is symmetry. We're going to see 3 types of symmetry. So you have x-axis symmetry, you have y-axis symmetry, and then you have rotational symmetry. And we'll say specifically with respect to the origin. So for x-axis symmetry, what we were going to want to check for is we're going to take our r theta and replace it with r negative theta and see if it gives us the same function. And then for y-axis symmetry, we're going to take our r theta and replace it with negative r negative theta. And for alpha point symmetry, we're going to take our r theta and replace it with r comma theta plus alpha. So our example here, we're going to take the r is equal to 5 sine 3 theta, and we're going to prove that that has both y-axis symmetry and 120-point symmetry. Maybe before we do that, let's just take a look at the picture and see what that looks like to see if we can observe that we have both of those 2 things beforehand. So there's the graph of 5 sine 3 theta. Look, it's a pretty flower. So certainly it's symmetric about the y-axis, right? If I look, the right-hand side is a reflection of the left-hand side. Everybody agree with that? And if I spun this thing 120 degrees, basically this pedal would move to that pedal moves to this pedal, and this pedal would move to that pedal. And you'd end up with the same picture, right? So certainly appears to have 120-degree point symmetry also. Everybody, visually that checks out. Tough to prove something that isn't true, so it's always worth taking a look at the picture and just making sure. All right. So let's go ahead and do that then. So I'm going to do these just in 2 separate columns here. For the y-axis, we're taking r theta and replacing it with negative r negative theta. So I've just taken my original function from the problem, and where the r, I put a negative r, and where there's a theta, I put negative theta. Everybody's okay? The goal now is going to be to simplify this down so that I get the original equation back. So 3 times negative theta is just negative 3 theta. Everybody's cool with that? Just a little multiplication there. And now I see an identity that I can use that would be quite helpful here. Take a look for a moment yourself. What identity do you suppose I would be using here?
I
Aiden?
forget what it's called, but you can just make a negative 5 sign.
Great. So Aiden says that sine of negative alpha is equal to negative sine alpha. That was one of the odd-even identities. And then if we just divide both sides by -1, we're back at our original. So we're good. So to do the 120 point or 120 degree point symmetry, I'm going to do nothing with r. That's just going to stay r. But in place of theta, I'm going to write theta plus 120 degrees. Well, I can distribute my 3 now. And, I see an identity that I can use here. Don't we have an identity for the sine of the sum of two angles? We do. So that identity says we get 5 times sine of 3 theta cosine 360 plus 5 cosine 3 theta sine 360. Actually, let's make that plus or minus. We'll do both formulas here. So that was the identity that I used there. Everybody still doing okay? What do you guys see that we can do now? Well, cosine 360 and sine 360, those are just unit circle values. I can just look that up, right? Oh, yeah, of course you can, Mr. Kulak. Awesome. What is cosine of 360? One! Right? You could type that in your calculator. You could use the unit circle, but it's just 1. Not unreasonable to if you shouted that out. You can picture the unit circle in your head where 360 is. It's easy to see where the x coordinate would be. Minimal memorization there. And then sine of 360 then has to be 0. So that whole piece just drops off because it's all multiplied by 0. And what am I left with? Oh my gosh! It's what we started with. Yes! Mr. Kulik, that was totally rad. I had a lot of fun. It was really satisfying. Do we feel okay doing this? They're very similar to the odd-even proofs we did in first semester, right? Ostensibly the same thing. So these graphs that we just, or the graph of something like this that looks like a flower, this is a whole actually class of polar functions that we're going to define right now called rose curves. Now, I've seen a lot of flowers in my day, but most roses don't look like that kind of flower that I just drew there. Don't ask me, I didn't pick the name for it. I don't know why they didn't call them daisy curves or something. Looks a little bit more peddly, but whatever. They didn't ask me when they named it. So the rose curves are of the form r is equal to a cosine n theta, or r equals a times sine n theta, where n has to be positive and an integer. Oh, actually, I should say greater than 1. So 2 or greater. So 2, 3, 4, 5, 6, 7, 8, 9. If it's 1, I think you just end up with a circle, which is not so exciting. Not very flowery, right? Okay, anyways. The domain for this, like any function that involves only sine or cosine, is going to be all real numbers. Oh, neato. The range for this is just going to be negative absolute value of a, comma, positive absolute value a. Notice that I had to put the absolute values there because if a was a negative number, negative a would be positive and your interval would be going big to small, which is wrong. So then obviously the minimum R value is negative absolute value a, and the maximum R value would just be positive absolute value a. The number of petals is always going to be n. And then as far as symmetries goes, there's 3 situations. In this symmetry situation, alpha is always going to be 360 divided by n. So like in the previous problem where we had 120-point symmetry, it's because there was 3 petals, so 360 divided by 3 gives me the 120. So if n is even, only one thing can happen. We get all 3 types. We get x-axis, we get y-axis, and we get alpha point. If n is equal to odd, and we have the cosine version, we have x-axis and alpha point. And then if n is odd, but we have the sine version, we have y-axis and alpha point. So if we ask you to like analyze r equals negative cosine 5 theta, I mean, you might want to start by just looking at the picture. Oh, look at that pretty flower. So I know right away this is a rose curve from the form, where the a is negative 6 and the n is 5. So I know the domain, because it's a rose curve, is going to be all real numbers. The range, because it's a rose curve, is going to be from negative 6 to positive 6, where I know the minimum is at negative 6 and the maximum is at positive 6. I know that there are 5 petals. And then the symmetries, since n is odd and we're the cosine version, we have x-axis symmetry, and in this case alpha is going to be 360 divided by 5, so that's 72 degrees. So we have x-axis and 72-degree point symmetries. How's that feel? Not a big deal, right? We're just using the facts from the chart, basically. Okay. There's another type of curve that we're going to talk about. And that's going to be the last thing that we have to talk about. And these are called limousin curves. So this word is pronounced limousin. It's somebody's last name. I don't know what that weird little C with the comma attached to it. What do we call that symbol? Does anybody know what we call that letter? I don't remember either. Somebody looked it up for me second hour, but I forgot already, which probably says how much I was paying attention when they told me what the answer was. But that's what's going on. So the standard form for a limousin curve is r equals a plus b cosine theta, or r equals a plus or minus b sine theta. But those a's and b's are both positive. So if there's a subtraction symbol attached to that b, that's part of the formula, not part of the value for b. Everybody's okay with that? Cool. All right. The domain, again, since it's just depending on sine and cosines, all real numbers. The range, well, it's going to be a minus b to a plus b. Where the maximum value is at a plus b and the minimum value is at a minus b. And now there are 4 types of limousin curves, and we can classify those 4 types by the ratio of a to b. So if A is less than B, that's going to be or A over B is less than 1, that's an inner loop. If A over B equals exactly 1, that's called a cardioid. If A over B is between 0 and 1, between 1 and 2, God bless it, is called dimpled. And for all other values, it's called convex. Let's just take a quick moment and I'll show you some pictures of what these look like. So doing this, I'm just going to turn the axes off because it'll give me a better picture. And I'm going to zoom in just a skosh here to -5 to +5, so it's a little bit easier to see what's going on. So how about 1 plus 2 cosine theta? There the A is 1 and the B is 2, so 1 over 2 is less than 1. This should be an inner loop. So there's see how the loop is on the inside of the circle thing? You guys see that? That's the inner loop. 2 plus 2 cosine theta, A over B is equal to 1. This is the cardioid. I think it looks a little like a heart or a butt. Okay. For this to be between 1 and 2, make it 3 over 2. So notice the dimpled and the cardioid look very similar. It's just how sharp of the crack is there. Really, though, this little indent's like, we call that indent a dimple, like on your golf ball. You know how your golf ball has little indents all over it? Those are called dimples. The same idea here. It's got one little dimple there. And then the last situation is convex. So like 4 over 2. If I graph this, there's no dimple anywhere, so it's just off the screen there a little bit to the right, but it's just basically a circle. There's no indents in it. It's not a circle exactly, but it's like there's no indented feature. Everybody feel okay? All right, we still need to talk about symmetry because there's two types or two situations for the symmetry. But it's really easy. So the cosine ones all have x-axis symmetry, and that's it. And the sine ones all have y-axis symmetry, and that's it. Okay. Example of this, and then we'll be outie. You guys happy? Okay. So if I look at the form, this is definitely a Lie-Masson curve, where the A is 4 and the B is 3. Remember, the B is always positive, no matter what the sign is in front of it. Okay. So I know that the domain here is all real numbers. The range, well, let's do the min and the max first. The minimum is A minus B. Oops. So 1. And the max is A plus B. So 7. So my range has to be from 1 to 7. The type, I noticed that we have 4 over 3 is the one that's between 1 and 2. So that was the dimpled. And the symmetry since we have the sine one, we have y-axis symmetry. And we're done. If you wanted to, you could take a peep at the picture here to see if it matches up with everything we wrote down. Oh, we'll make our window a little bit lower there. That ought to capture it. Yep. So there's my dimple right there. Still kind of looks like a butt. Everybody happy? All right. Let's be done here for today. Just FYI, at this point, you guys can now finish up and do 63 to 96. We're planned for Thursday is going to be the review day. And then we're going to start chapter 11, the next class, and then take the chapter 10 test the following one. I did that because the drama students this week didn't want to do the test this week on Friday. So we were just bumping it into next week for them, since they seemed like they had a lot going on this week. Okie doke? Yeah.